Okay, now we're doing the last bit of our content here, section 4.6 to 4.7, solving exponential and log equations. And we're also going to have some applications in on this too. You may have some questions on your homework or need some videos done up for that. I will provide solutions for most of them, but you may need more details than that. If there's more complex problems that you come across, feel free to ask me to do some of those too. So we have things to know. First thing we want to think about is exponentiating both sides of an equation, or which we've looked at before during exponentials, or take the log of both sides of an equation. Okay, exponentiate just means that you're doing this action here. So if you have equivalent exponents, if y equals x, then b to the y equals b to the x. So you can raise to a power or make something have a base as long as it's the same base. Same thing here, you can take the log of both sides here, log base b of y equals log base b of x. This is all based on the properties, and especially in that intro, how we do the kind of exchanging from one form to another. And this is kind of like the shortcut for that as well. You can only do this when you have equations. That's kind of the trick there. So just like the rules for simplifying linear equations, when we clear denominators, say for instance on fractions, on rational equations, we can't do that if we just have an expression on one side, because there's nothing to balance, okay, unless we have like fractions within fractions. So that's the thing. You have to either, if it's just an expression, you can multiply top and bottom by the same thing. That's okay, but you can't just like kind of wipe it out. And also on this, you can't just take the log of one side. You would have to take the log of both sides, so you have to do it on an equation to balance. So I can't stress that enough. And also you can't use log properties unless you actually have done the log, taking the log of both sides. That's one thing I've noticed too. Sometimes people start using properties, but they haven't written that actual log in there. So the last statement here, remember, we have to have x and y being greater than 0. So that's important too. This means we should only introduce logs when both sides of the equation represent positive values. Also, if we eliminate logs by exponentiating, we could introduce an extraneous solution. We will always check for extraneous solutions when solving a log equation. So that's another thing too that's important to note, that just like when you, I think it was you were squaring to solve like a radical equation, you were squaring both sides, you had to check for extraneous solutions because you had to make sure the sides balanced, because whenever you're playing around with it like that, you need to be careful. All right, so let's get into some of the examples here. And this, I think, is the fun part. You get to use your skills, your properties, and kind of play with it. It's sort of like a puzzle, if you think of it that way. Like, how can I manipulate this to get what I want? So if I have log base, it looks like it's a base 10, right? So common log, because there's nothing there, of x equals -3. So that's important to note, that this is really a base 10. Because what undoes that, we need to do the inverse operation, right, on both sides, which is exponentiating. We need to use the appropriate base, which will be 10. So I can exponentiate both sides, and I'm going to rewrite this though for you. I usually just kind of stick a 10 there, but this really means 10 log base 10 of x. I'm just writing that in so it's clear. And then 10 to the negative third. And I can do that because I have this situation there. So I have these set equal to each other. So now I can undo this. Becomes 1, or just x, right? Just the x value. So I have x equals 10 to the negative third. Okay, so in this case, I can just calculate that out to be x equals 1 over 1,000, or I could write it as 0.001. Either one of those would be fine. And we need to check the domain, and we're good. We have x is greater than 0. So check domain. X is greater than 0, so we're good, okay? So on this one, we have a base of an x. So let's see how you do with that. Go ahead and try that for classwork. Do the same process. So you're going to exponentiate. So you're going to have the base of your exponential be x, and then you're going to make this part be the exponent, which is kind of weird. So we have this y value equals x from up here. So we can, again, exponentiate each side of that, and we're staying true to our equivalency, is what that means. So at any point, whenever I say classwork versus example, you can do them all as classwork and then check your answers. Do make sure you're checking. I'm not collecting notes this time around. I want you to reflect on it. I hope that doesn't encourage you to not actually write stuff out, but what I'm hoping is that you'll write it out. You'll try a lot on your own. You'll check them. You'll ask questions, and you'll write a little reflection in there. You'll answer, yes, I know this is important and I'm accountable to it, but also that if there's something you come across, you can, let me know, that was hard for me or whatever, and I can write back to you. But if you need to get something to me right away, either email me or write in the comments so that I see it. I check my email a lot and get notifications and stuff. So I'm going to do x to the log base x of 81 equals x to the 4th. Don't forget to do both sides, right? And then here this will become just the 81 equals x to the 4th. And how we tackle that, we just take the 4th root of both sides, or we could think of it as this. We could raise it up to the 1/4 power, which is the same thing as taking the 4th root of both sides. But do remember that we have a plus or minus situation. However, we want all our x values to be positive. So because our base needs to be positive. Back in the beginning in the intro to logs, remember b has to be positive. So we have the 4th root of 81 is going to be 3. This undoes, so x equals 3. And we're good because our base, not our domain, but our base is positive. Now let's take a look at some others here where we start with an exponential on this one. So what undoes exponentials would be log. So if I want to take the log of one side, I have to take the log of both sides. So we're going to do log base 3 of 3 to the x equals log same base, has to be same base, of 7. Now that leaves us with x equals log base 3 of 7. And I'm having you leave this as an exact answer, not crunching it out. You could use a calculator at this point to find a numerical answer. You would use your change of base formula if you didn't have a calculator that could handle the base of 3. But for these type of problems, we want exact answers, but decimals are okay for word problems. So I'll specify that on tests. Okay, so I just wrote you a little note here. Leave like this for skill work since it's an exact answer. For word problems, you can calculate it out and round. And again, you can use your change of base, or graphing calculators will do different bases for you. Probably the TI 36 Pro will do that too. So now let's look over to the right. And this one is log that we want to undo. So we're going to exponentiate and make it have a base of a half. So we're going to raise this up. So we're going to write a half raised up to log 1/2 2x plus 1. And then equals a half raised up to log base half x plus 3. Now, sometimes people notice, okay, these are equal, so can I just set those equal? And in this case, you can, because they're just together. But I want to show you why that works. Okay. But there are some cases where you have to be much more careful than just taking some shortcuts. So really notice the differences amongst these. So then we have 2x plus 1 equals x plus 3. And it's just a regular equation to solve. We'd have x plus 1 equals 3, x equals 2. Just make that look a little better. Okay, so we get x equals 2 for this, but we do need to check a couple things. We want to make sure that works for our domain. If we put 2 into this one, we get 2 times 2 is 4 plus 1 is 5. So we're good there, and we're also good here. 2 plus 3 would give us 5. And when I'm doing that, I'm checking the equivalency also. So 2 times the 2 plus 1, does that equal 2 plus 3? So I'm checking domain and equivalency kind of simultaneously. So I do get 5 equals 5. So if I did log base half of 5, log base half of 5, I would get the exact same answer. So I'm good there. Okay, I want you to try these two for classwork and see how it goes. It's base E, so you're just doing natural log instead of log. You don't have to do log base E. You don't have to write that. Just write ln for natural log. So these two are going to be classworks. And then I'll write out the solutions. So think about what kind of process you're going to take. And then check back. Okay, so I wrote up the solutions for these. E to the 4 minus x equals 11. And then we have take the natural log of both sides. So we end up with 4 minus x equals natural log of 11. Do some manipulating here. You got to subtract 4 from both sides and then change each to its opposite. Now be careful here. You have to distribute that negative, whether I'm dividing through or multiplying through. And so I end up with x equals negative ln 11 plus 4. Sometimes we don't like that negative in the front, so we can write it as 4 minus ln 11. In my domain, I would have to have all real numbers as my exponent, and that is a real number. So we're all good there. On this other one on the right-hand side, we started with natural log of 11x equals natural log of x minus 5. So we can exponentiate and raise each of those up to, write base E and make these logs be the exponent. So we're undoing those. We're just left with our exponent. So we have 11x equals x minus 5. And then solve it out. We get x equals negative a half. So the problem there is that we end up with a negative in the that we're taking a log of, and we can't have that. That's not in the domain. So we would cross that out. That's extraneous, and we have to write our answer as no solution. So if you don't actually come full circle and do this part, you won't get full credit. You'll lose a point. So make sure you understand that. If you have any questions on that, let me know. But it just goes back to what we've always worked on. Something has to be in the domain for it to actually be a solution. And if there isn't any that work, then just write no solution. I'll leave it hanging. So now this one is okay to work with here as one unit because it's all in parentheses. We don't have them separated out. So we can actually just exponentiate each side. If you want to try that on your own, go ahead. It's a quadratic that it comes out to be. So this would end up being x squared plus 5x plus 10 equals 2 to the 4th, which is 16. So then we end up, we have to solve it out. You can pause and do that on your own if you want. X squared plus 5x minus 6, that equal to 0. Then we can factor. We get x plus 6, x minus 1 equals 0. So set each factor equal to 0. We get x equals negative 6 or x equals a positive 1. And then we have to check and make sure that we don't get any negative values in here because this original problem was just the log of that. So we want to check. And you can just check quick that we have negative 6 squared plus 5 times negative 6 plus 10. We get 36 minus 30 plus 10. So I'm good there. I just make it I get 16. And then the other one, I have a 1. So I have 1 squared plus 5 plus 10. And I also get 16. So that works. Now this one on the right hand side, I have 10 to the x squared minus 1 equals 24. So in this case, since I start with an exponential, to undo that, I need to take the log of both sides. So I'm going to take the log of 10 to the x squared minus 1. And the log of 24 on the other side. So if I do common log base 10, that will just leave me with the exponent here, x squared minus 1 equals log base 24. Add 1 to both sides to get my square alone. So I'm going to get log base 24 plus 1. And then I'm going to take the square root of both sides. And I'm left with x equals plus or minus square root log of 24 plus 1. And that's a base 10 common log. If you wanted to just see what those values were, you could do that. And plus or minus is okay here because when I put that in, I'm going to square it. And plus I can have real numbers in my exponent. It's fine. All right, so that is almost the last one. Here's the last one. We have base, it's 2 log base 3 of x equals log base 3 of 2x. So we're not quite there because we don't quite have a match. So we can't just say like, oh, let's exponentiate right off the bat. We have to just have a clear log ready. It has to be simplified first. So we're going to use our property and rewrite this as log base 3 of x squared equals log base 3 of 2x. Then we can exponentiate, raise each to the, or have a base of 3, and those will undo each other there. So then I have x squared equals 2x, and I can go ahead and factor this. X squared minus 2x set equal to 0. X times x minus 2 equals 0. You could probably pause and finish this out, but I have x equals 0 or x equals 2. Well, I have logs here, so I can't have a 0. It has to be greater than 0. So this one is extraneous, and this one is my answer. Okay, this is not in germane. All right. And if I put the 2 in there, I would actually balance because I would have a 2 squared and a 4 over here. So that works too. So that's it for this first part of the log equations video. So I'm going to stop there and start up a new video for the next one. So have a great day.